We've seen that we can use geometry to find the area underneath a curve. We also found that if the shape we were trying to find the area of wasn't a shape like a rectangle or a triangle, that we could approximate that area by using rectangles. And that the more rectangles we used, the closer the approximation would get to the actual area. Now we also said that we can express that area by using a definite integral. In this case, the definite integral is from -1 to 2 because those are the least and the greatest x-coordinates of all of the points in the bounded area, and the top curve of this bounded area is described by x squared plus 1. Now what if we want the exact area, not an approximation? Well, we can use the definite integral to find that exact area. Here's how we're going to do it. The first thing we'll do is find the antiderivative of the function f of x. In this case, find the antiderivative of x squared plus 1. Now we can use any antiderivative of that function, so we'll choose to use 0 for c, which means in this case the antiderivative is x to the third over 3 plus x. The second step is to evaluate that antiderivative at the two numbers that are the lower and the upper bounds for our integral, and then subtract those values. That means we'll substitute 2 into our antiderivative and -1 into our antiderivative, and then subtract those two values. So there's a lot of arithmetic to be done at this point. But once we do all that arithmetic, we end up at a value of 6, which means the exact area underneath this curve is 6 square units. So let's see how that works with some other functions. Let's say we'd like to find the integral from 0 to 3 of e to the x dx. We're looking for the area under the graph of e to the x that has x-coordinates between 0 and 3, and that also is above the x-axis. The antiderivative of e to the x is e to the x, and we're going to evaluate that at 3 and at 0, and then we'll subtract those two values. Now there isn't a lot more to be done here except to say that e to the 0 is equal to 1. So the area underneath the curve is e to the third minus 1. What if we want to find the area under the curve y equals x cubed over the interval from 1 to 2? Well, this is what that graph would look like. And this is what the integral would look like. The integral from 1 to 2 of x to the third dx. The antiderivative of x to the third is x to the fourth over 4, and we're going to evaluate that at 2 and at 1, and subtract those two values. Once again, we have a lot of arithmetic to be done, but once we do all the arithmetic, we end up with a value of 15/4. So the total area underneath the curve, y equals x to the third, between the x values of 1 to 2, and above the x-axis, is 15/4. Let's try this one. Find the area under the curve, y equals x squared minus 8x plus 11 over the interval from 2 to 5. So we're going to integrate from 2 to 5, x squared minus 8x plus 11. The antiderivative is x to the third over 3 minus 4x squared plus 11x, which we're going to evaluate at 5 and at 2, and then subtract those two values. So we'll substitute 5 for all of our x's, and we'll substitute 2 for all of our x's. And once again, lots of arithmetic to be done to simplify. And we end up with a value of -12. Now that might seem a little strange. We're finding area under a curve and we've found a negative area? That doesn't really make sense, does it? A negative area actually does make sense if you think about what the graph of this function looks like. We're finding this area that's bounded by the curve and the x-axis and the vertical lines x equals 2 and x equals 5. Now, if you think about what we did when we were approximating area with rectangles, we found that the height of the rectangle was determined by the y-coordinate of the point where that rectangle intersected the curve. And in this case, all of those y-coordinates would be negative. So if we multiply those y-coordinates times the width of the rectangles, we're going to get negative numbers. So what we see here is that if we have an area that's underneath the curve, that area is going to be a negative number. So we could summarize that by saying that the area that's above the x-axis will always have a positive value, and that area below the x-axis will always have a negative value. So think about this. If this function has a graph that looks like what you see up above, is its area going to be positive or negative? Is the value of the integral going to be positive or negative? Well, since there's more area above the axis than below the axis, the total area is going to be positive. How about this one? Will its total area be positive or negative? Well, since more of the graph is below the x-axis than above, the total area is going to be negative. And how about this one? Will its total area be positive or negative? Well, since the same amount of area is above and below the x-axis, the total area would be 0. So now let's find the area under the curve y equals x squared minus 4 over the interval from -1 to 3. We'll integrate x squared minus 4 to give us x to the third over 3 minus 4x. Then we'll evaluate at 3 and at -1 and subtract those values to finally reach a value of -20 So what does that mean? Does that mean that the entire graph, the entire bounded area is below the x-axis because we got a negative value? Well, no, it doesn't. It just means that there's more of the area below the x-axis than above the x-axis. So let's try one last problem. Felix the cat is not happy when he has to travel to the veterinarian. The rate at which he meows while in his carrier in meows per minute is given by m prime of x equals -1/3 x squared plus 18. How many total times does Felix meow in the first 6 minutes of his ride to the vet? So the function we're given is a rate at which he meows, and we would like a function that describes the total number of meows. So we need to find the antiderivative of the rate function, and we need to evaluate that from 0 to 6 to get the total number of times he meows in the first 6 minutes. Well, the antiderivative is negative x to the third over 9 plus 18x. We'll evaluate that at 6 and at 0 and subtract those values. And we find we have a value of 84. So Felix is going to meow a total of 84 times in the first 6 minutes of his ride to the vet.